Hello, everyone, and welcome to a Soundbite from The Sound of Science,
a shorter installment of Oak Ridge National Laboratory's podcast series.
In our last episode, we discussed the strange world of quantum mechanics.
The laws of quantum mechanics describe the odd behavior of subatomic particles.
Harnessing the power of quantum mechanics could create a technological revolution.
While quantum technologies might sound like something out of science fiction, the reality is quantum applications in computing, materials, sensors, and networking could have a profound impact on our everyday lives.
Scientists at ORNL are working to advance quantum technologies in these areas.
Nick Peters is one of those scientists. He leads the lab's Quantum Information Science group and has been working on using quantum to improve network security against cybersecurity threats.
When you encode information in a quantum object, it's really fragile. And the fact that it's fragile means that you can't copy it without ruining it. You can't measure it and understand exactly what it was. And because of that, it sort of is naturally eavesdropper proof. So if somebody tries to eavesdrop on it, it will mess it up. And that'll be detected by the two people that are trying to carry out the quantum security protocol.
Nick and his group have been focusing on improving network security for the power grid through technology called quantum key distribution.
Quantum key distribution is really one of the more mature quantum technologies. And what we're doing is trying to show that there's a really strong use case for implementing it for grid security. And reasons why we're doing that is that when you deploy grid technology, you want it to last a really long time. And so if you want it to last a really long time, then it makes sense to deploy it along with security technologies that are going to last a really long time. And so quantum is one of those security technologies which potentially lasts forever.
Quantum key distribution, or QKD, harnesses the power of quantum mechanics to distribute secret keys that can be used to authenticate data and encrypt messages. Using these methods, the key is used to lock information for transmission from one QKD system to another through what's called a trusted node.
Traditional cybersecurity technologies rely on classical cryptography, and that can only last so long because technological advances make it possible to crack the computational codes, so to speak. But quantum offers a different approach that doesn't have an expiration date. Even if technology advances, the laws of quantum still offer protection.
Assuming that you do it right, the laws of quantum mechanics aren't going to change, so it'll stay secure indefinitely.
The long-lasting nature of this technology makes it very appealing for use on the grid, because unlike smartphones and laptops that generally require replacement every few years, swapping substations or generators that often would be impractical and expensive.
The motivation behind a lot of this work is the fact that we're modernizing the grid infrastructure. And if you put your grid infrastructure on the internet, that means now something that previously you had to just sort of drive up to have access to it, you can now access if you've got a computer connected to the internet anywhere in the world. And so what that does is it opens up potential problems. And so if we have a really strong cybersecurity posture, it sort of heads those problems off before they develop.
To put this technology to the test, Nick and his team have been working with EPB, a utility company located in Chattanooga, Tennessee.
We're working with EPB to go show that these systems, even though they're difficult to repair, actually work in realistic environments. So our demonstration showing that we can do trusted relays in the grid infrastructure is the first such demonstration. And it's significant in that these grid environments are not necessarily very well controlled like our laboratories are. And so there's a lot of electromagnetic interference, potentially big temperature swings, and showing that it works in these realistic environments is actually something that is important from the quantum side so that we can believe that our technology will eventually work. But it's also important from the vendor and the utility side because they don't want to see technologies roll out that aren't tested. They like to know that you can integrate them and that their systems will still work the same way that they used to, but now they've got an enhanced capability.
So what exactly does this kind of technology actually look like?
So the actual equipment that we have, it's on the order of the size of a bread box. And you have to have two of these bread boxes. One is a transmitter and one's a receiver. And then you connect them right now with today's current technology, typically with a piece of glass that's an optical fiber. And because the quantum technology of today is pretty sensitive to noise sources, we basically dedicate the entire fiber for just that single photon quantum transmission. So one of the things we're trying to do is we're trying to develop technologies where you can instead put that single photon quantum transmission along with other classical signals that would typically propagate along optical fiber. The problem is that the optical fiber itself, it's a scattering medium, so that when the classical signals come through, it creates noise that can totally swamp your quantum signal. And so what we're doing is we're developing new concepts where, by virtue of how we do it, it basically eliminates all that noise from impacting the quantum signal. And so if we can do this, it makes the operation cost dramatically cheaper, because classical data that's carried on these fibers is a valuable commodity.
The advances being made in quantum technology at ORNL are just a preview of the exciting things to come out of the field.
I think the most exciting thing that's going to happen in the next few years is we're going to start to see some quantum technologies that actually result in substantial improvement over what we're able to do with classical technologies. That's kind of going to be the watershed moment. And we've kind of had some things like quantum key distribution where we can do things now that you cannot do classically. But there's still a lot of open questions about what's possible and what's the best way forward. And so that's really the role of the national lab in trying to figure this out. Is there's a lot of real basic science that people need to figure out to make this technology practical and really be usable by a much wider part of society.
Thank you for listening to this soundbite from The Sound of Science.
Be sure to subscribe to the series wherever you get your podcasts, so you get new episodes as they're released.
Until next time.